carbon moves around throughout the environment. And one of the big issues in climate science is how much of it sticks around in the atmosphere. The atmosphere has 730 gigatons of carbon in it, but that is increasing at 3.2 per year. So approximately 0.5% per year, we're increasing this atmospheric carbon pool. If we tried to rebalance the system, eventually all this extra carbon, let's say we do what we're doing now for 10 years, and we put 30 gigatons in the atmosphere. It's going to be an imbalance in the system. The atmosphere is going to have too much carbon in it. Eventually, it will move into the big sink for carbon, the ocean. But that process is slow. It takes thousands of years. So the drivers of the increase in the CO2, the greenhouse gas, one of them is per capita energy use, which has increased eightfold over 150 years. That's a good thing, right? This is people's living standards going up. Right? If you can do this with low carbon fuels, that's even better. Right? And here's population growth. And I don't want to get into an argument whether that's a good thing or a bad thing. This isn't the place for that. But these two signals multiplied together cause this rapid increase in the amount of carbon dioxide in the atmosphere. It doesn't look so rapid until you make a little longer view of things. Right? So here's the long view. Here's a 10,000-year view of CO2. 260 parts per million. Doesn't sound like a lot. It's not. But then we hit the Industrial Revolution, and we're going up at 1 to 2 parts per million per year. So over a 100-year period, 2 times 100 is 200 parts per million. So in 100 years, we can potentially double the amount of CO2 in the atmosphere. How do they know what CO2 was in the atmosphere 10,000 years ago? These are from deep ice cores, where they extract air that was trapped in the snowfall and analyze it for CO2. A little review of our list of forcings. First, I talked about 3 natural forcings. Orbital variation, big but slow. Takes tens of thousands of years at a minimum. Variation in the brightness of the sun, important but small over the last 200 years. Volcanic aerosols are important, but there's nothing we can do about them, and they're kind of random. And then this man-made anthropogenic forcing, carbon dioxide. This is from the Intergovernmental Panel on Climate Change. This is their longer list of forcings. So I talked about the ones with the purple stars. So CO2. Things on the right of this line are positive forcings. They make the climate warmer. Things to the left are negative forcings and cool off the atmosphere and the surface. So I talked about CO2, which is the biggest of the positive forcings, and I talked about solar irradiance. There's other forcings, methane, N2O. These are different refrigerants and fire suppressant gases. We have ozone, and then you've got your aerosols, which is the other thing that I study, is what controls the concentration of these aerosols. Now, aerosols are bad to breathe. We learned that during the Beijing Olympics, where people made a big deal about how polluted the city was. And our cities were that polluted 50 years ago, and we've cleaned them up. So as a solution to climate change, polluting everything so that those aerosols will cool things off is not a good solution, because you'll kill hundreds of thousands of people and shorten their lives and give them respiratory disease. So that's not going to happen. These are going to be cleaned up in city after city after city as these developing countries get their economies together and these technologies in place. So I would argue that this number can't go up that much because these aerosols are pollutants and we won't tolerate them. This number just goes up and up and up because the CO2 that we emit stays in the atmosphere for hundreds or thousands of years. When I emit a particle, it stays in the atmosphere for a week until it rains and it falls out. So if you add these up, the total forcing right now is positive. It's 1.5 plus or minus 1. And then it's increasing because of the CO2 that's continually building up. So that's what I want to say about things that affect the climate. Now I'm going to talk about the observed climate system. This is the global average temperature anomaly. So this is the other term I have to define. It's very hard to measure the global average temperature itself. It's about 17 degrees centigrade. But where do you measure that? Do you measure that a millimeter off the ground, or a foot off the ground, or 2 meters off the ground? You know, do you do it in the shade? Do you do it in the sun? If you have a temperature station and somebody builds a shopping mall next door, how does that affect things? So there's all these complications with measuring the global average temperature. So one of the things that's done is that you have a long-term record at a station, and there's several of them in Iowa. And what they do is they take the average temperature from 1950 to 1980, and then they compare everything against that. And if there's major land use changes around the station, they either modify the record or drop the station off the list. So that's why these are anomalies. So this is the difference in temperature compared to 1950 to 1980. There's several of these records. They're all pretty similar. This happens to be NASA's. And the verdict is a 0.8 centigrade, or a little over a degree Fahrenheit increase in the global average temperature over this 120-year period. So these are measurements. So they're difficult measurements, and people argue about the accuracy of them, but they are measurements. And most people use these as the starting point for, yes, the climate has changed. Here's 3 different records. They all look the same. This is this 0.8 to 1 degree increase. Air temperature over land, air temperature over sea at night, sea surface temperature. Sea surface temperature is a different measurement. You stick a bucket in the ocean and measure that temperature. So the fact that all these things are doing the same, this would indicate that it's not the fact that we just built shopping malls next to every land station. As you urbanize a station, the dispersal of that urban heat changes some of the temperatures at the station. But if you look at high wind speed events where the urban center heat is dispersed well, and low wind speeds, you get the same slope, the same increase over time. So that's a sign that urbanization isn't polluting that record. So that's the global average, but where did it warm? It didn't warm equally everywhere over that period. So the average has to be 0.8, right, which is yellow. And what we've seen is less intense warming in large ocean basins, more intense warming in the northern hemisphere poles. This is one of the features that's predicted by the climate models. Other observed features are heavy 3-day rainfall events. And yeah, you'd like to do this globally, but most of the measurements are in northern mid-latitudes, so this is Europe and the US. Right? Percent change from 1961 to 1990. And there is a trend in more intense 3-day rainfalls. Another measurement is glacier retreat. There's no arguing that glaciers have retreated. These are Alps glaciers. This is the length of the glacier, so a glacier is a tongue of ice going down a valley, and you can measure its length, and sometimes they grow when it's cold and there's a lot of snowfall. Sometimes they shrink when there's a lot of melt. So on average, glaciers have been melting. I have the requisite glacier photos. So here's Muir Glacier, 1941. Muir Glacier, 2004. McCall Glacier, 1958. McCall Glacier, 2003. And these aren't cherry-picked. This is all glaciers, and that was the example of 2 of them. Arctic sea ice decrease. This is 1970 to 2005. This happens to be how many million kilometers square change. So we've been losing sea ice. The sea level has risen. So these are measurements as well. And you see these are different places around the world. And you see, yeah, there's a lot of variability. But you see a small upward trend in most of these stations. Tropical storm. So this is the power dissipated by all storms over a year, right? And that's been going up. So predicting climate is one of the things that is key to raising the alarm bell. So if scientists predict how things are going to go over the next 100, next 200 years, and are concerned, well, these are some of this is, I'm going to try to explain how these predictions are done. So you need input to your computer model, computer simulation of the global climate. You need emissions of the different gases and particles. Those give us the concentrations of these different forcing gases. Then you have to know how much temperature change you get from those forcings. The temperature change is linked in with the entire climate system, which includes rain, clouds, sea level, glaciers. And then you need to forecast how this is going to change things that matter to people, like intense rainstorms, droughts, periods of intense heat, periods of intense cold, so on and so forth. So the climate system, these are things that have to be included in your computer model. I don't know if there's people that play these computer games like SimCity, but it's like a giant version of SimCity where you've got a computer model that includes a description of sea ice all over the globe, a computer model that includes a description of ocean temperatures and ocean flows all over the globe, clouds, solar radiation, your greenhouse gases. These generate, there's physics behind the energy transfers in this system. Those physics have equations. Those equations are solved and forecast the state of the system moving forward. And while it's impossible to forecast the weather 10 days from now, you can forecast the climate 10 days from now, which is the average weather. You can go to the National Weather Service and find out if the next 2 months are going to be drier than normal, wetter than normal, hotter than normal, or colder than normal. So when you do this, one of the things that you get out of your computer model is a model simulation temperature of this global anomaly that I showed. So that's the green band. So you put in the known volcanic eruptions over the past 100 years. You put in the best numbers that you can get for the sun intensity over the past 100 years, and you get these kind of temperatures in green. Here's the measurements in red. Now I've cheated. They've only included natural forcings here. So none of the man-made forcings are included in the model. Because most people are saying, well, the green and the red don't match.